So let's look at the importance of dimensions and units. Any physical quantity can be characterized by dimensions, and the magnitudes assigned to these dimensions are called as units. So some basic dimensions such as mass, usually depicted by the letter M, and length by letter capital L, time, letter simple t, and temperature, letter capital T, are used as primary or fundamental dimensions. And then there are dimensions such as velocity, capital V, energy, capital E, and volume, capital V, are expressed in terms of primary dimensions, and these are called as secondary dimensions because they are expressed in terms of primary dimensions, and these secondary dimensions are also called as derived dimensions. So there are two systems of units that are used throughout thermodynamics. One would be the metric or the SI system, and it is basically a simple and a very logical system based on decimal relationship between various units. And then there is the English system that is sometimes referred to as the imperial or customary system, and that basically has no apparent systematic numerical base. And the various units in this system are related to each other in a rather arbitrary manner. In this text, we will be primarily using the metric SI system, but of course there would be some problems associated with the English system as well. So let's look at some SI and English units. As you can see, 1 pound mass lbm English units would be equal to 0.4536 kilograms SI units, and for 1 foot English units would be equal to 0.3048 meters SI units. And throughout this course you will have to use this equation F equals ma whenever you want to find the force whenever a mass and acceleration is given. And in terms of SI units, you would notice that in order to generate 1 Newton of force, you would accelerate 1 kilogram by 1 meters per second squared. And in terms of English units, in order to generate 1 pound force, you will have to accelerate 32.174 pound mass by 1 feet per second squared. And also you will have to use this equation that has to do with force, distance, and work. Of course, in order to find work, you will have to multiply force by the distance it traveled. And you will also notice that work done could be measured in any of these units, which could be joules, calories, or BTU. So let's look at dimensional homogeneity. In engineering, all equations must be dimensionally homogeneous. That is, every term in an equation must have the same unit. If at some stage of an analysis we find ourselves in a position to add two quantities that have different units, it is clear that we made an error at an earlier stage. So checking dimensions can serve as a valuable tool to spot errors in our calculations. Now let's look at what unit conversion ratios are. Just as all non-primary dimensions can be formed by suitable combinations of primary dimensions, all non-primary units, which are also called as secondary units, can be formed by a combination of primary units. Force units, for example, in SI can be expressed as 1 Newton would be equal to 1 kilogram meter per second squared. They can also be expressed more conveniently as unity conversion ratios as 1 Newton divided by 1 kilogram meters per second squared would be equal to 1. Unity conversion ratios are identically equal to 1 and are unitless. And such ratios or their inverse can be inserted conveniently into any calculation to properly convert units. With dimensional homogeneity in mind, try problem 1 and then problem 2. So based on dimensional homogeneity, you will notice that the units for Q, W, MH and U are going to be the same, and also it is going to be the same for this long expression 1 and also this long expression 2, and also the units are still going to be the same for delta U, delta KE and delta PE. And when you calculate the answers for the second problem, you will notice that the units for L is going to be ns squared, whereas the units for X is going to be ns squared over kilogram or per kilogram. So using the knowledge that you have acquired thus far on dimensional analysis and unity conversion ratios, try to convert 453.6 grams into newtons. If you did the calculation right, you will notice that 453.6 grams would equate to 4.49 newtons.